A Formula One car is a single-seat, open-cockpit, open-wheel racing car with substantial front and rear wings, and an engine positioned behind the driver, intended to be used in competition at Formula One racing events. The regulations governing the cars are unique to the championship. The Formula One regulations specify that cars must be constructed by the racing teams themselves, though the design and manufacture can be outsourced. Construction. Chassis design. The modern-day Formula One cars are constructed from composites of carbon fiber and similar ultra-lightweight materials. The minimum weight permissible is 702 kilograms including the driver but not fuel. Cars are weighed with dry weather tires fitted. Prior to the 2014 F1 season, cars often weighed in under this limit, so teams added ballast in order to add weight to the car. The advantage of using ballast is that it can be placed anywhere in the car to provide ideal weight distribution. This can help lower the car's center of gravity to improve stability and also allows the team to fine-tune the weight distribution of the car to suit individual circuits. Engines. The 2006 Formula One season saw the Fédération Internationale de l'Automobile introduce a then-new engine formula. Further technical restrictions, such as a ban on variable intake trumpets, have also been introduced with the new 2.4 LV8 formula to prevent the teams from achieving higher RPM and horsepower too quickly. The 2009 season limited engines to 18,000 revolutions per minute, in order to improve engine reliability and cut costs. For a decade F1 cars had run with 3.0-litre naturally aspirated V10 engines. However, development had led to these engines producing between 980 and 1,000 horsepower, and reaching top speeds of 375 km per hour on the Monza circuit. Teams started using exotic alloys in the late 1990s, leading to the FIA banning the use of exotic materials in engine construction, and only aluminium, titanium and iron alloys were allowed for the pistons, cylinders, connecting rods, and crankshafts. The FIA has continually enforced material and design restrictions to limit power. Even with the restrictions, the V10s in the 2005 season were reputed to develop 980 horsepower, which were reaching power levels not seen since the ban on turbocharged engines in 1989. The lesser-funded teams had the option of keeping the current V10 for another season, but with a rev limiter to keep them from being competitive with the most powerful V8 engines. The only team to take this option was the Toro Rosso team, which was the reformed and regrouped Minardi. The engines consume around 450 L of air per second. Race fuel consumption rate is normally around 75 L, 100 kilometers traveled. All cars have the engine located between the driver and the rear axle. The engines are a stress member in most cars, meaning that the engine is part of the structural support framework, being bolted to the cockpit at the front end, and transmission and rear suspension at the back end. In the 2004 championship, engines were required to last a full race weekend. For the 2005 championship, they were required to last 2 full race weekends, and if a team changes an engine between the 2 races, they incur a penalty of 10 grid positions. In 2007, this rule was altered slightly and an engine only had to last for Saturday and Sunday running. This was to promote Friday running. In the 2008 season, engines were required to last 2 full race weekends, the same regulation as the 2006 season. However, for the 2009 season, each driver is allowed to use a maximum of 8 engines over the season, meaning that a couple of engines have to last 3 race weekends. This method of limiting engine costs also increases the importance of tactics, since the teams have to choose which races to have a new or an already used engine. As of the 2014 season, all F1 cars will be equipped with turbocharged 1.6-litre V6 engines. Turbochargers have been banned since 1988. This change may give an improvement of up to 29% fuel efficiency. One of the many reasons that Mercedes dominated the season early was due to the placement of the turbocharger's compressor at one side of the engine, and the turbine at the other. Both were then linked by a shaft traveling through the V of the engine. The benefit is that air is not traveling through as much pipework, in turn reducing turbo lag and increases efficiency of the car. In addition, it means that the air moving through the compressor is much cooler as it is further away from the hot turbine section. Transmission. Formula One cars use semi-automatic sequential gearboxes, with regulations stating that 8 forward gears and 1 reverse gear must be used. With rear-wheel drive, the gearbox is constructed of carbon titanium, as heat dissipation is a critical issue, and is bolted onto the back of the engine. Full automatic gearboxes, and systems such as launch control and traction control, are illegal. To keep driver skill important in controlling the car, the driver initiates gear changes using paddles mounted on the back of the steering wheel, and electro-hydraulics perform the actual change as well as throttle control. Clutch control is also performed electro-hydraulically, except to and from a standstill, when the driver operates the clutch using a lever mounted on the back of the steering wheel. A modern F1 clutch is a multi-plate carbon design with a diameter of less than 100 mm, weighing less than 1 kg and handling around 720 horsepower. As of the 2009 update race season, all teams are using seamless shift transmissions, which allow almost instantaneous changing of gears with minimum loss of drive. Shift times for Formula One cars are in the region of 0.05 seconds. Changing a gearbox before the allowed time will cause a penalty of 5 places drop on the starting grid for the first event that the new gearbox is used. Aerodynamics. Aerodynamics have become key to success in the sport, and teams spend tens of millions of dollars on research and development in the field each year. The aerodynamic designer has two primary concerns: the creation of downforce, to help push the car's tires onto the track and improve cornering forces, and minimizing the drag that gets caused by turbulence and acts to slow the car down. Several teams started to experiment with the now familiar wings in the late 1960s. Race car wings operate on the same principle as aircraft wings, but are configured to cause a downward force rather than an upward one. A modern Formula One car is capable of developing 6 grams lateral cornering force thanks to aerodynamic downforce. The aerodynamic downforce allowing this is typically greater than the weight of the car. That means that, theoretically, at high speeds they could drive on the upside-down surface of a suitable structure, e.g., on the ceiling. Early experiments with movable wings and high mountings led to some spectacular accidents, and for the 1970 season regulations were introduced to limit the size and location of wings. Having evolved over time, similar rules are still used today. In the late 1960s, Jim Hall of Chaparral first introduced ground effect downforce to auto racing. In the mid-1970s, Lotus engineers found out that the entire car could be made to act like a giant wing by the creation of an airfoil surface on its underside, which would cause air moving relative to the car to push it to the road. Applying another idea of Jim Hall's from his Chaparral 2J sports racer, Gordon Murray designed the Brabham BT46B, which used a separately powered fan system to extract air from the skirted area under the car, creating enormous downforce. After technical challenges from other teams, it was withdrawn after a single race. Rule changes then followed to limit the benefits of ground effects. Firstly, a ban on the skirts used to contain the low-pressure area. Later, a requirement for a step floor. Despite the full-sized wind tunnels and vast computing power used by the aerodynamic departments of most teams, the fundamental principles of Formula One aerodynamics still apply. To create the maximum amount of downforce for the minimal amount of drag, the primary wings mounted front and rear are fitted with different profiles depending on the downforce requirements of a particular track. Tight, slow circuits like Monaco require very aggressive wing profiles. You will see that cars run two separate blades of elements on the rear wings. In contrast, high-speed circuits like Monza see the cars stripped of as much wing as possible, to reduce drag and increase speed on the long straights. Every single surface of a modern Formula One car, from the shape of the suspension links to that of the driver's helmet, has its aerodynamic effects considered. Disrupted air, where the flow separates from the body, creates turbulence which creates drag, which slows the car down. Look at a recent car and you will see that almost as much effort has been spent reducing drag as increasing downforce from the vertical end plates fitted to wings to prevent vortices forming to the diffuser plates mounted low at the back, which help to re-equalize pressure of the faster flowing air that has passed under the car and would otherwise create a low-pressure balloon, dragging at the back. Despite this, designers can't make their cars too slippery, as a good supply of airflow has to be ensured to help dissipate the vast amounts of heat produced by the engine and brakes. In recent years, most Formula One teams have tried to emulate Ferrari's narrow waist design, where the rear of the car is made as narrow and low as possible. This reduces drag and maximizes the amount of air available to the rear wing. The barge boards fitted to the sides of cars also help to shape the flow of the air and minimize the amount of turbulence. Revised regulations introduced in 2005 forced the aerodynamicists to be even more ingenious. In a bid to cut speeds, the FIA robbed the cars of a chunk of downforce by raising the front wing, bringing the rear wing forward and modifying the rear diffuser profile. The designers quickly clawed back much of the loss, with a variety of intricate and novel solutions such as the horned winglets first seen on the McLaren MP4-20. Most of those innovations were effectively outlawed under even more stringent aero regulations imposed by the FIA for 2009. The changes were designed to promote overtaking by making it easier for a car to closely follow another. The new rules took the cars into another new era, with lower and wider front wings, taller and narrower rear wings, and generally much cleaner bodywork. Perhaps the most interesting change, however, was the introduction of movable aerodynamics, with the driver able to make limited adjustments to the front wing from the cockpit during a race. That was usurped for 2011 by the new DRS rear wing system. This too allows drivers to make adjustments, but the system's availability is electronically governed. Originally it could be used at any time in practice and qualifying, but during the race could only be activated when a driver is less than 1 second behind another car at predetermined points on the track. The system is then deactivated once the driver brakes. The system stalls the rear wing by opening a flap, which leaves a 50 mm horizontal gap in the wing, thus massively reducing drag and allowing higher top speeds, but also reducing downforce, so it is normally used on longer straight track sections or sections which do not require high downforce. The system was introduced to promote more overtaking, and it has become frequent to be a cause of overtaking on straights or at the end of straights, where overtaking is encouraged in the following corner. However, the reception of the DRS system has differed among drivers, fans and specialists. Former Formula One driver Robert Kubica has been quoted of saying he has not seen any overtaking moves in Formula One for 2 years, suggesting that the DRS is an unnatural way to pass cars on track, but it does not actually require driver skill to successfully overtake a competitor. Therefore it would not be overtaking. The use of aerodynamics to increase the car's grip was pioneered in Formula One in the late 1960s by Lotus, Ferrari and Brabham. Wings' early designs linked wings directly to the suspension. but several accidents led to rules stating that wings must be fixed rigidly to the chassis. The car's aerodynamics are designed to provide maximum downforce with a minimum of drag. Every part of the bodywork is designed with this aim in mind. Like most open-wheel cars, they feature large front and rear aerofoils, but they are far more developed than American open-wheel races, which depend more on suspension tuning. For instance, the nose is raised above the center of the front aerofoil, allowing its entire width to provide downforce. The front and rear wings are highly sculpted and extremely fine-tuned, along with the rest of the body, such as the turning vanes beneath the nose, barge boards, side pods, underbody, and the rear diffuser. They also feature aerodynamic appendages that direct the airflow. Such an extreme level of aerodynamic development means that an F1 car produces much more downforce than any other open-wheel Formula Indy cars. For example, produce downforce equal to their weight at 190 km per hour, while an F1 car achieves the same at 125 to 130 km per hour, and at 190 km per hour the ratio is roughly 2 to 1. The barge boards in particular are designed, shaped, configured, adjusted and positioned not to create downforce directly, as with a conventional wing or underbody venturi, but to create vortices from the air spillage at their edges. The use of vortices is a significant feature of the latest breeds of F1 cars, since a vortex is a rotating fluid that creates a low-pressure zone at its center. Creating vortices lowers the overall local pressure of the air, since low pressure is what is desired under the car, as it allows normal atmospheric pressure to press the car down from the top. By creating vortices, downforce can be augmented while still staying within the rules prohibiting ground effects. The F1 cars for the 2009 season came under much questioning due to the design of the rear diffusers of the Williams, Toyota and the Brawn GP cars raced by Jenson Button and Rubens Barrichello, dubbed double diffusers. Appeals from many of the teams were heard by the FIA, which met in Paris before the 2009 Chinese Grand Prix, and the use of such diffusers was declared as legal. Brawn GP boss Ross Brawn claimed the double diffuser design is an innovative approach of an existing idea. These were subsequently banned for the 2011 season. Another controversy of the 2010 and 11 seasons was the front wing of the Red Bull cars. Several teams protested, claiming the wing was breaking regulations. Footage from high-speed sections of circuits showed the Red Bull front wing bending on the outside, subsequently creating greater downforce. Tests were held on the Red Bull front wing, however the FIA could find no way that the wing was breaking any regulation. Since the start of the 2011 season, cars have been allowed to run with an adjustable rear wing, more commonly known as DRS. A system to combat the problem of turbulent air when overtaking. On the straights of a track, drivers can deploy DRS, which opens the rear wing, reduces the drag of the car, allowing it to move faster. As soon as the driver touches the brake, the rear wing shuts again. In free practice and qualifying, a driver may use it whenever he wishes to, but in the race, it can only be used if the driver is 1 second, or less, behind another driver at the DRS detection zone on the racetrack, at which point it can be activated in the activation zone until the driver brakes. Ground effect F1 regulations heavily limit the use of ground effect aerodynamics, which are a highly efficient means of creating downforce with a small drag penalty. The underside of the vehicle, the undertray, must be flat between the axles. A 10 mm thick wooden plank or skid block runs down the middle of the car to prevent the cars from running low enough to contact the track surface. This skid block is measured before and after a race. Should the plank be less than 9 mm thick after the race, the car is disqualified. A substantial amount of downforce is provided by using a rear diffuser which rises from the undertray at the rear axle to the actual rear of the bodywork. The limitations on ground effects, limited size of the wings, and vortices created by open wheels lead to a high aerodynamic drag coefficient, so that, despite the enormous power output of the engines, the top speed of these cars is less than that of World War II vintage Mercedes-Benz and Auto Union Silver Arrows racers. However, this drag is more than compensated for by the ability to corner at extremely high speed. The aerodynamics are adjusted for each track, with a low drag configuration for tracks where high speed is more important like Autodromo Nazionale, Monza, and a high traction configuration for tracks where cornering is more important, like the Circuit de Monaco. Regulations. With the 2009 regulations, the FIA rid F1 cars of small winglets and other parts of the car used to manipulate the airflow of the car in order to decrease drag and increase downforce. As it is now, the front wing is shaped specifically to push air towards all the winglets and barge boards so that the airflow is smooth. Should these be removed, various parts of the car will cause great drag when the front wing is unable to shape the air past the body of the car. The regulations, which came into effect in 2009, have reduced the width of the rear wing by 25 centimeters, and standardized the center section of the front wing to prevent teams developing the front wing. Steering wheel. The driver has the ability to fine-tune many elements of the race car from within the machine using the steering wheel. The wheel can be used to change gears, apply rev limiter, adjust fuel, air mix, change brake pressure, and call the radio. Data such as engine RPM, lap times, speed, and gear is displayed on an LCD screen. The wheel hub will also incorporate gear change paddles and a row of LED shift lights. The wheel alone can cost about $50,000, and with carbon fiber construction, weighs in at 1.3 kilograms. In the 2014 season, certain teams such as Mercedes have chosen to use larger LCDs on their wheels, which allow the driver to see additional information such as fuel flow and torque delivery. They are also more customizable owing to the possibility of using much different software.